Hi everyone, welcome to lesson 2. This lesson is going to be pretty heavily vocabulary based. You can see on the screen right now some terms that we're going to be using. Natural numbers, whole numbers, integers, rational numbers, irrational, and real numbers. What I will say right now is you have used probably all of these types of numbers already, and now it's kind of a matter of putting words to a type of number that you should already be familiar with. We're going to talk about categorizing numbers and identifying which type a number might be and which group a number might belong to. We'll see some diagrams, and then we'll answer some questions related to sets of numbers. So a set is just a group of numbers. Usually there's something in common with all the numbers in a set, but not always. So before I kind of talk us through this slide here, I am going to actually immediately switch over to the whiteboard. So normally what I would do in a regular class is I would write on the actual whiteboard on one side, and then I'd have the vocabulary terms on the other side to kind of compare. So I'm going to do a version of that right now. So the screen's going to be blank, and we'll come back to this vocabulary screen soon. All right, let's switch over to the whiteboard. Okay, so to take us through all the different kinds of numbers, I'm going to start from the beginning. Think about when you first learned about numbers. You were probably very small, you probably don't even remember it, but at some point in your life you learned to count. So we'll start there. And I'm going to be making a certain kind of diagram right now. And you don't have to make it look exactly like mine. And in fact, there's other versions of this on the PowerPoint that we'll get back to, but I think it's nice to be able to kind of walk through it together. So do your best to kind of draw your own version of this as we go along. So this is going to be sort of circles, sort of one circle inside another. I'm going to start with what are called natural numbers or counting numbers. Okay, so 1, 2, 3, etc. Dot, 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 going on forever. These are the counting numbers. They start with 1. We do not start counting with 0, okay? So natural numbers start with 1 and go up from there. Notice what's not in this list. There's no 0, no negatives, no fractions, no decimals, just plain old counting numbers. So just think about what you've learned when you were very, very small, what you first learned. This is the most basic set of numbers. And then we're going to grow the sets beyond this now. So at some point, then you learned that there was this number called 0. All right, so the next set of numbers does include 0, and it also includes 1, 2, 3, etc. This set of numbers is called the whole numbers. So notice that the set of natural numbers is contained inside the set of whole numbers. Every natural number is also a whole number. An example of this kind of category is everybody in Omaha is automatically also in Nebraska. It does not work the other way. Everybody in Nebraska is not necessarily in Omaha. So every whole number is not necessarily a natural number. One group is smaller than the other. Let's continue adding on. So the whole numbers include 0, 1, 2, 3, etc. Beyond that, let's start acknowledging the fact that there are negative numbers. So once we start including negative numbers, that's when we get into integers. So integers include 0, 1, 2, 3, as well as -1, -2, -3, dot, 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 etc. So it's very possible that when you see these numbers, this might be what you think of as whole numbers. A lot of times people use the word whole to mean just not a fraction or decimal. But integers includes all these other kinds. So it does include 0, it includes 1, 2, 3, etc., positive numbers. It also includes negative versions of those. So In a way, the set of integers includes the natural numbers as well as the negative natural numbers, sort of one way to think about it. Or I sometimes call these numbers the number line numbers. If you were to sketch out a number line, this is usually what we label on the number line. 0 in the middle, then positives to the right, negatives to the left. Okay, from here, now we get into more complicated kinds of numbers, including what we just learned in our first lesson, fractions, as well as decimals. So these are rational numbers. Now the word rational has the word ratio in it. The word ratio can mean fraction. A ratio is a fraction. It's a comparison of two numbers. I've also heard the phrase, rational numbers are fractional. So there's no way I can list all of the rational numbers. That process kind of breaks down. We can never possibly list all the fractions and decimals. So I'm going to give you some examples. -1/2, +2/3, decimals, 5.2. We could do 0.3 repeating. So repeating decimals are part of this as well. Any decimal that ends or repeats is considered a rational number. Any fraction, positive or negative, including mixed numbers. Here, let's do a mixed number, 6 1/7. There you go. That's a rational number. And all these other numbers that we already listed are also rational. These could all be written as fractions. If we just put them over 1, suddenly it's a ratio, it's a fraction. And any decimal that either repeats or ends could be written as a fraction if we needed to. We're not going to really focus on that right now, but just know that it could be done. Okay, so I'll just underline these as well. So by underlining, if you can't really tell what I'm trying to do here, is I'm trying to show that the sort of these inner groups are also part of the outer groups as well. So for example, this number 1, it is a natural number. It's also a whole number. It's also an integer, and it's also a rational number. So back to the Omaha, Nebraska example, you might be in Omaha. So if you're in Omaha, you're also in Nebraska. If you're in Nebraska, you're also in the United States. If you're in the United States, you're also in North America, etc. So the groups kind of grow and grow and grow, but you can't say the opposite, right? So if you're in North America, there's no guarantee that you're in the United States. If you're in the United States, there's no guarantee that you're in Nebraska, etc. Okay, so some groups fit inside the others, but not the other way around. Okay, so one more example. Let's see, say maybe the number -2. It's an integer and it's rational, but it is not a whole number and it is not natural. Okay, so just notice kind of the different layers of groups here. All right, now there's a couple other types of numbers that I'm going to try to squeeze in here. Way off to the side, the misfit numbers are called irrational numbers. So anything that's not rational, we would call irrational. This includes numbers like pi. Let's see, square roots, such as the square root of 2. What else? You're going to see some decimals that kind of look like they repeat, but they don't quite. So here's an example, 1.45455, and I'm running out of room here, 4555. I could continue a pattern, but it's a non-repeating, non-terminating decimal. Terminate means end. So non-repeating, non-terminating decimals. So pi, you may have learned possibly in an algebra or geometry class, pi is 3.14, but it's really not 3.14. It's much, much longer than that. It's 3.14159 and many, many, many more digits after that, literally going on forever. So it's a non-ending or never-ending decimal, and there's no pattern to it. It's non-repeating. Same thing with a square root, like the square root of 2. If you have a calculator and you try to find the square root of 2, your entire calculator screen will be taken up by a decimal that has no pattern to it. It is not repeating, and it would be never ending if it weren't for your calculator screen ending. Okay, so these are some, not all examples obviously, but these are some examples of irrational numbers. Now, all of these numbers together are real. Okay, so I'm just going to write the word real to include all, here, we'll group everything, everything that we're talking about, rational as well as irrational. These are all real numbers. Now there are numbers that are not real. Those are called imaginary numbers. We do not talk about those in this class, so you'll have to just wait. I think in college algebra you learn about imaginary numbers. So yes, that is a thing that you learn about in a math class. You learn the word imaginary, but not in this class. So right here you have kind of a basic visual illustration of the different types of real numbers. And we'll talk more about what are we going to do with these numbers, what do we need to know about them, etc. So I will save this little image here and you can find it. I'll put it as an attachment to go along with the video. If you didn't notice it already in Blackboard, it should be there as you're watching this if you'd like to download it, but otherwise hopefully you were able to just kind of take notes along the way. All right, I'm going to go back to the PowerPoint now. Okay, so I kind of like going through these terms with that visual process that we just saw, but here we are. I'll get through the actual slideshow now. Okay, so here we are with the actual list of terms and definitions. I tried to cover all of this in that diagram I just went through with you, but just a quick recap, natural numbers are also called counting numbers. So naturally we start with 1, 1, 2, 3, 4, 5, and so on. Whole numbers, now we're adding 0, so it's the natural numbers plus 0. 0 looks like a whole, so feel free to use that as a way to remember. Integers, those are kind of the number line numbers here. I'll just make a little note of that, number line. Just a little way to remember. Rational numbers are fractional, or see I underlined the ratio there, so fractional. Rational numbers are fractional. It does include most decimals, okay, as long as they either end or if they repeat. Those are rational numbers. If they don't end and don't repeat, that's when they are irrational numbers. So pi was an example of an irrational number. It's a never-ending, non-terminating, and non-repeating decimal. So other examples include square roots that don't simplify, such as the square root of 2, square root of 5, etc. Little bit of a trick question that comes up sometimes. Something like the square root of, let's say, 9. The square root of 9 is 3. That's a natural number. Okay, so be careful. If you see a square root symbol, make sure, see if you could actually simplify it. The square root of 9 is 3 because 3 squared is 9. These are things that I haven't taught you in this class, but I'm hoping you've seen before, exponents and square roots. So if you're not familiar with this, please just ask, or maybe we'll go over it in one of our live meetings if we need to. You could use a calculator to check that out as well. But if the square root doesn't come out to a nice number like 3 or 5 or any kind of whole number, it's an irrational number. So it's one or the other here. And then putting all these groups together gives us the real numbers, the set of all numbers that can be represented on a number line. So not just the ones we imagine on a number line, but everything in between. So not just 0, 1, 2, etc., -1, -2. But it's everything, okay? So all those in between numbers that we couldn't possibly label all of them, it's all of those are the real numbers. So it includes rational and irrational numbers. All right, and then on the next slide here, we have some other diagrams similar to what I showed you a few minutes ago. So these are different ways you can see that certain groups kind of fit inside other groups, natural, whole, integer, rational, and then irrational off to the side. Here's another one, natural, whole, integers, rational, irrational off to the side, and then the whole thing is real. So here's some more examples. This one's interesting. It's more like a tree diagram where it starts with the real numbers and then it kind of splits things off into groups. So that's not usually how I picture it, but I thought that was an interesting diagram. I copied this from another colleague. Rational, irrational, and then there's integers or non-integers. negative integers, whole numbers, and then 0 and natural. So whichever kind of clicks with you and helps you to keep track of the different types. These visuals can help, or the list of vocab is there as well. I just like the visual as well. Okay, so what are we going to have to do? We haven't solved any problems yet today. We haven't answered any questions. What will we be asked to do? Okay, so let's see. Now, I think I'm going to actually skip ahead in this PowerPoint because this slide right here, I took these questions from the homework. I think since it's fresh in our minds, I'm going to skip ahead and let's talk about categorizing types of real numbers. We'll go back to the previous slide in a moment, but those questions are kind of in sort of a different category. So let's use what we just learned about types of real numbers, and let's see if we can take this really long list of numbers, this long set of numbers, and we will categorize each one. So it says, given the following set, list each type of real number below. So they're listed in order. Let's start with natural numbers. So when we look carefully in our list here, which ones are natural? Remember the counting numbers, starting with 1, 2, 3, etc. Okay, -2, no. 0, not a counting number. 36, if we kept counting, we would eventually get to 36. Let's see, this is meant to be 1 decimal. I realize there's a space there. That's meant to be 6.05, so that's not natural. I wouldn't count with that one. Square root of 81. All right, so square root of 5, if you know how to do the square root function on your calculator, which I know we're technically not using calculators yet, but I know you have one around or you have a phone. The square root of 5, it's a never-ending decimal, okay? So that is not a natural number. However, the square root of 81 is actually 9 because 9 times 9 is 81. So I will list that here as a natural number. So it's kind of a natural number in disguise here. I think that's it. What we have left in our list, we have a mixed number, we have a fraction, and then we have this really long, never-ending decimal. Okay, so I think this is it for our natural numbers. Now what I'm going to do is I'm going to recognize that anything that's a natural number is also a whole number. So I will just automatically put these in my list for whole numbers. Because remember, anything that's a natural number is also a whole number. That group was contained inside the other one. Okay, so whole numbers now, we start with 0, but we still continue counting beyond that. Okay, so speaking of which, let's add 0 to our list here. 0 is a new addition. All right, so we have natural numbers, and then the whole numbers, it's all the natural numbers plus also 0. Integers, now it's going to be all those whole numbers, 36, square root of 81, 0, as well as, okay, what were the integers? Maybe at this point you're referring back to your notes. This is all new. I'm going to switch back to a previous slide just to remind myself about what the integers were. Let's see, here are the integers. These are the number line numbers, right? So it's the whole numbers plus, oh yeah, plus the negatives of those whole numbers. So -1, -2, -3, etc. Okay. So do we see any numbers like that? Here's one, the very first one on our list. -2 is an integer. 0 we already have, 36 we have. We don't want any decimals or fractions or square roots, except for the square root of 81, which was 9. Okay, so this is my list of integers now. So these are the number line numbers. Okay, so -2, -1, 0, 1, 2, 3, etc. Okay, rational numbers. This is going to be a nice long list. Okay, so rational numbers are fractional. So any fraction will be in this list. Also, all these integers as well. So I think I'm going to run out of room here. I'm going to start with listing all the integers first. 36, square root of 81, 0, -2. And now let's add to that list. Okay, I'm going to carefully go along here. 6.05, that's a decimal that does end. It does not go on forever, so that is a rational number. This is 6 5/100. That's how I would write that as a fraction, 6 5/100. Still don't want that square root of 5. That's going to be irrational. I have the square root of 81. I do want this 7 and 1/7, any kind of mixed number. That's a kind of fraction, so that would be in our list. And then the negative 23/7, also in our list. This last decimal, this is the one I was referring to before. I found this one really tricky when I looked at it because it does kind of look like it's repeating. There's a pattern to it, but it doesn't count as repeating. A repeating decimal would be something like 1.454545, etc. You might write that with 1.45 with a bar over it. That would, I'll just off to the side, just note that would be rational because it would be repeating. The 4545 would be repeating. This is not repeating. It's 45, 455, 4555, 4555. The fives will just continue to grow. So this is non-repeating. And based on the ... right here, it's also non-terminating. Oops, go back. Non-terminating or never-ending. Just abbreviate there. Okay, so I will not put that in my list of rational numbers. Instead, let's continue and answer the irrational numbers. So nothing that I have listed yet should be in this group. The irrational numbers are just all by themselves. Okay, totally separate group. Okay, so what have we not put in our list yet? The square root of 5, that is a non-repeating, non-terminating decimal. The square root of 81 was 9. I already listed that, so that's not in this list. The only other one is this 1.45, etc. Now, on the homework, you'll be able to just choose it as a multiple choice option without having to worry about typing it out. Oops. Sorry about that. When I get near the end, it keeps thinking I want to be done. So let me get us back to that slide here. Oh, we can see it okay. All right. All right, so we're almost done with that particular slide. Let's just get back to it so we can see it better. There it is. All right, and then real numbers. Every single number in this list is real. So we would just copy each one down, or on the homework, you'll just select all of them. Okay, so I'm just gonna save us some time. I'm gonna say all. So all of these are real. You will not be given any numbers in this class that are not real. In case you're wondering, those would be imaginary. They would involve a little lowercase I. We will not be covering that in this class. Some of you may have heard of those before. I'm guessing most of us have not, which is fine. So just nice, easy question. If you're asked if a number is a real number in this class, you just get to say yes automatically. All right, now I skipped a slide, so let's go back. These other questions are a little bit different. We're being introduced to something called roster notation and set builder notation. It already sounds harder than it is, I promise, okay? A roster, think of a class roster, it's a list, that's all. So these first two questions, I hope that you'll find they're easier than you might expect. So roster notation, you're just making a list. Okay, now there's some brackets set up for you. Probably seen that before in math where we have a set of something, a group of something, we use these squiggly brackets. I'm going to name a set with all the letters in the word mathematics. It's just listing the letters. Okay, so the one trick to this, I guess, if there's a trick, if you see any repeated letters, don't list them more than once in your answer. So let's write this out together, and I hope you'll see that this really isn't that bad. Okay, so M, I'm putting a comma because this is a list. I'm just making a list of the letters in the word mathematics. M-A-T-H. T, H, E, and then here's another M. I'm not going to repeat it. And then here's another A. I'm also not going to repeat that, and same thing with the T. So just no need to rewrite those letters because they're already included in the list. So with a roster, you just include everything exactly once in the list, and then we're left with these last three letters, I, C, and S. So kind of a strange question. That's just called roster notation. Number 2, we're going to use roster notation to name the set. All odd whole numbers less than 11. Okay, so review, odd numbers are not divisible by 2. 1, 3, 5, 7, 9, 11, etc. And there, did I just give us the answer? Almost. Whole numbers, remember, whole numbers, that's 0, 1, 2, 3, 4, 5, 6, etc. Starting with 0. Okay, 0 is even, 2 is even, 4 is even, 6 is even. So we're not including even numbers, we're including odd numbers. Okay, so let's just start with the first odd whole number, which is 1, then a comma. 3 is the next one, 5, 7, 9. Now there's this instruction here about being less than 11. I actually do not want to include 11 because 11 is not less than itself. 11 can't be less than 11. So if it said less than or equal to 11, then I would include it, but I'm not going to include it. So that's it. This is all the odd whole numbers less than 11. That's all. All right, so that's called roster notation, making a list. These next couple examples are using something called set builder notation. So we're describing a set of numbers in these different ways. Let's start with what we see here. The wording here would be the set of all x such that, let me type that out here. I would write it, but my handwriting is not the best on this. So the set of all x such that is how we're meant to read this. Okay, so that's, let's see, I'm gonna go back here. Oops. All right. Yeah, so this line right here, what we say is such that. Okay, so we're starting with a little bracket. This is basically saying what's in the set. And what's in this set is x. Okay, that's maybe not that helpful. I need more information. Okay, what are we going to say about x? X means just a number that's unknown. I need more information. Such that, okay, we're about to get some information. So let's read more. X is an integer, so everything in the set is an integer, and now we have a little fill in the blank job to do. Okay, let's look at the actual set here. -2, -1, 0, 1, 2, 3, 4, 5. So think about in your own words, how would you describe the numbers in this set? Just not even in a math class, just to the person next to you. How would you describe? What are the numbers in the list? Oh, okay. Oh, it's all the numbers between, maybe what I would say is between -2 and 5. But that's not quite what we're going to answer here because these symbols right here don't have equal signs. So let's think about it this way. What would be the next number in the list if we were to keep going? -2, -1, 0, 1, 2, 3, 4, 5, 6, right? Everything in this list is less than 6. That's going to go here. That's kind of like the upper bound or the upper boundary of the set. And then everything in the list is greater than, what would be the number over here? Well, that would be -3. That's all. I know this seems strange and there's a lot of new symbols going on. This is honestly not the most important part of this lesson. I'm putting these examples here because they did happen to show up in your homework. The important part was the vocabulary we were talking about before, with all the different kinds of numbers. So if you're feeling stressed out about these new symbols, try to just not overthink it. Don't worry too much. I know that's easy for me to say. Don't overthink it. These numbers are just between, you might think of it as between -2 and 5, but we're not including We're not including our endpoints with these symbols. There's no equal sign, so we need to go one beyond that. So all these numbers are, we'll say greater than -3. That's what that part is saying. So x is greater than -3, or -3 is less than x, if you read it left to right. And what else? Less than 6. And it's important that we're not just saying numbers, we're saying integers, right? So there's no fractions or decimals in this list. Okay, I think there's one question like that on the homework, and then you'll be able to move on. All right, let's do one more example here, then I'll take you over to some MyLabs Plus problems just to show you what you'll be asked to do. Okay, number 4, the set of all x such that x is a whole number, okay, 0, 1, 2, 3, yep, those are whole numbers, less than or equal to, okay, if it just said less than, all these numbers are less than 4. But this time we do get to include our answer, right? So, or equal to. So the numbers in this list are either less than 3 or equal to 3, right? This last one is equal to 3. So I do get to say 3 for my answer. So notice the difference between those two problems. If there's a less than symbol or greater than symbol without an equal sign, you don't want to include your numbers. And then if there is the word equal to, then you do want to include your answer. Okay, so feel free to pause here or take a short break if that's what you need. I am now done with the notes portion here. In a regular class, I would now be giving you some practice and say, okay, here's some problems to try, or here's some other examples for you to do on your own and for us to go over. So I might give you maybe a classwork worksheet or something. Instead, what I'm going to do right now is take us to the MyLabs Plus homework and show you some of those examples just to kind of solidify what we just learned and make sure you understand what we're doing here. All right, but if that was enough for you, feel free to be done and come back to the video later if you need it. Let's see, so we're now looking at our list of assignments. Let's look at homework number 2, the set of real numbers. And there's 16 questions here. Okay, so number 1, roster notation. That was that making a list. We just did it with the word mathematics. We're using roster notation to name the set of all letters in the word plus. Okay. Use a comma to separate answers as needed. It's, I hope, easier than you might think, to the point of you might be asking, why am I doing this? Good question. You're just getting introduced to the concept of making a list. So P, comma, L, comma, U, comma, S. There we go. Okay. Number 2, use roster notation to name the set of all, let's see, even whole numbers less than 10. Okay, so whole numbers would be 0, 1, 2, 3, 4, etc. Those are whole numbers. But even numbers would be divisible by 2. So that would be 0, 2, 4. We'll keep going. So 0, 2, 4, 6, 8, 10, 12, etc. But we want them to be less than 10. Okay, so if I want the numbers that are less than 10, I can't include 10 and definitely not 12 or anything beyond it. This is my list right here. So these are the even whole numbers less than 10. Okay, and then I would go ahead and type those. Use commas to separate answers and type in ascending order. Ascending means going up, so it means least to greatest, like how I did here. Okay, so this is the exact answer I would type in. I'm just going to keep on moving and look at our next set of questions here. Let's see, number 3, set builder notation. Use set builder notation to name the set. 0, 1, 2, 3, 4, 5, 6. Those look like whole numbers to me. So let's take a look. Okay, so the set of all x such that X is a whole number, yep, less than or equal to 6. In our notes, the example had 3. In my homework, I would just type 6 here. Okay, good. So my goal right now is just to give you a little preview of some of these questions here. Okay, set builder notation to name the set 9, 10, 11, 12, 13. Okay, here we have some multiple choices. Let's see. They all involve whole number. Yep, these are whole numbers. They're also natural numbers. That's fine. Let's see. I think I need to choose choice A because it's not just greater than something and it's not just less than something. It's not going on forever in either direction. So I think I need to name something on either end of the set. So these numbers are all greater than something and less than something. Okay, so I'm looking at the 9 and the 13, but let's see what happens if I type those numbers in. I'm gonna get it wrong, but let's just see what error message will we get if we try that. Okay. Not something super helpful. When using set builder notation, instead of listing all numbers in the set, conditions under which a number is in the set are specified. Determine how to describe a number X in the given set. Okay, well, that's fine, but that doesn't really help me that much knowing why I'm wrong. But as you may remember, we don't have the word equal here. So I don't want to include the number 9. 9 is not greater than 9. The next whole number would be 8. So all the numbers in this set are greater than 8. Most of them are less than 13, but 13 isn't less than 13. So I would put 14 as my next answer. So that's basically the next numbers that would have been in the list would be what I would put there. Okay. Good, and now we're getting to the bulk of what our lesson was here, where we're categorizing numbers. Okay, so I'm not going to do all of these because some of them are pretty similar, but let's just get an idea of how we might be asked to answer these. So here's number 5. Given the following numbers, name the natural numbers. So just remember, natural numbers are counting numbers. 1, 2, 3, 4, etc. So do we see any counting numbers here? What would we eventually count to? And we can actually just run down the list where it says select all. It's the same list. I just get to check off anything in the answer. So 21 is a counting number. I would eventually get to 21 if I were to count. Nope, not going to count to that decimal. 0 you might consider as an answer, but remember, 0 is not a counting number. It is not a natural number. That is a whole number. Okay, I'll continue down my list. No fractions, no negatives. Square root of 4, trick question here. The square root of 4 is 2 because 2 squared is 4, or 2 times 2 is 4. So yes, I do have to check that one for a natural number. I think that's it. None of these other ones look like anything I would count to. Okay, now once again, I do want to show you what it would look like if you missed this. So let's say I checked 21, but I forgot to check the square root of 4. It says at least one of your answers is incorrect and or you have not selected all of the correct answers. Okay, so it reminds me about the set of natural numbers. That's fine, okay. And now I'll know to check that one. Okay. So we're going to see other questions like this with different categories of numbers. This one is whole numbers, so it's essentially the same idea, only this time we would include 0. This time, there's a lot of times there's 2 or 3 square roots and one of them is a whole number or a natural number. In this case, it's the square root of 1, which is 1. 0 is a whole number, and then any counting number, yep, 22, that would also be an answer there. Okay. Good. Next, we'll be asked about integers. So it's asking you in the same order that we went over them in the notes. So that's good. For the sake of time, I'll just keep going here. Irrational. Okay, this is a good one. Irrational. Those are the ones that are kind of the misfit numbers. Okay, those are Those are in a group to themselves. Misfit. Not a technical term, but that's how I think of them. So they are non-repeating and then non-terminating decimals. They go on forever. All right, so there will not be many things that we get to check off for this category. Let's see, a fraction would be rational. So no, don't check that one off. Choice B, square root of 13. The square root of 13 is not a nice number. It's not a whole number. So that means it is irrational. So I will check that one. Choice C, this little bar here indicates that it's a repeating decimal. So since it's repeating, it's rational. So it's all good. I do not want to check it. Remember, I'm looking for non-repeating decimals. This is repeating. Okay, square root of 9, that's 3. So that is a natural number. It definitely does not go on forever and it does not repeat. It's just 3 or 3.0. So I'm not checking that one. 25, negative 1/2. Okay, this square root of 7 right here, it has a negative in front. Still, it's irrational, whether it's negative or positive. This is another square root that does not come out to a nice number. It's a non-repeating, non-terminating decimal. Let's keep going. Choice I, this decimal has an end to it, so I will not be choosing that one because it is a terminating decimal. It has a termination right here. Choice J, we saw one kind of like this in the notes. This is non-repeating, non-terminating. It does not repeat. I know it kind of looks like it does, but that list of ones will just continue to grow and grow and grow forever, and it does not end. Okay, and I think that is it. So that's a nice long list here. 16.999, that ends. Okay, so don't choose that one. We're only choosing non-repeating, non-terminating decimals. So be on the lookout for square roots, especially, and then this kind of weird looking decimal right here that goes on forever but doesn't repeat. Those are the irrational numbers. Okay, good. Let's see what else we got. Next one is rational. I think I just clicked similar exercise by mistake. Let's see. No, I didn't. Okay, so we did, sorry about that. We did number 8, irrational. Number 9 would be rational. Okay, so that would be everything except for the irrational numbers. Real, this one, just check all of them. All of these are real. Name the real numbers. So for number 10, you would check all the real numbers. Everything is real on these lists. Okay, number 11, it looks like now we're being asked to type the answers. Name the natural numbers from the list below. Okay, counting numbers. I see 48 is a counting number. I will not be naming 0. And then the square root of 4. I'm going to try something. What if I call it 2? Let's see if it'll accept that answer. Yeah, that's fine. That's okay. Now I'm going to do a similar question just to see. I just reshuffled the numbers. I click similar question down here. Natural numbers, this time it would be 40. And if I want to type the square root of 81, I can click on this square root button and then type 81. So it looks like you can simplify the square root or you don't have to. Either one is fine for those natural numbers. Whole numbers, same idea. Integers, we get to check from a list. Irrational, okay, now they're giving letters, so you don't have to type them out. Type the corresponding letters. So irrational, let's see, negative 20, 0, 9, 8.13. Right here, square root of 15, here's the first one, but I'm just gonna type the letter E. Square root of 100 is 10, that's a whole number, or natural number, or integer, or rational number. It's in a lot of groups, but it's not irrational. It is not a never-ending decimal. It's not a non-repeating, non-terminating decimal. So don't choose square root of 100. 3 1/3, 25, 27s, those are fractions, which means they are rational. So don't choose those. The other one you would choose is this decimal here, which is choice I. That's not a 1, that's an I, capital I. Okay. Good. The only type we haven't gone through right now is rational, which is number 15. And then what's number 16? just to get a little preview. Real numbers, that's good. That's good. Just check them all. So the last one we'll do together is, let's do one with rational numbers. This is number 15. So when you see the word rational, get ready to check most of your choices. In fact, it might be easier to just eliminate the ones you won't be choosing. Okay, so anything that's irrational, I'm going to cross out. This is irrational. That decimal going on forever, non-repeating, non-terminating. Square root of 6, irrational. Cross that out. Everything else in this list is rational. The square root of 100 is 10, so that's a nice number. That's a natural number, which means it's whole, it's integer, and it's rational. Anything that's a fraction is good. Any decimal that ends is good. Negatives are fine. 0, yes. This is a whole number, which means it's also rational. Mixed number, that's also a choice. So with rational, I find it easier to identify the irrational numbers, cross those out, and then just check everything else. Okay. Good. All right, so I'll check my answer here. All right, I think that's good. So that's our lesson 2. If you're watching this, I believe lesson 3 is assigned on the same class day as lesson 2. So take a little break, and then I would say get right back in and take a look at the lesson 3 video as well. We would be covering both of those in the same class period. So, okay, let me know if you have any questions. Thank you.